Okay, so same idea here. Hopefully you've printed out the notes and template for this video and have looked through it and looked through the text, because I'm just going to go through some of the examples. This is usually a chapter that people need a little bit more time to work through and get used to. Uh, when we talk about estimating a population mean, we need to talk about a new distribution called a t-distribution. We got to look at t-curves. People for years have been using just a z-curve, a standard normal approach, and an employee working for Guinness Brewery realized that, hey, we're not getting the reliability that we expect, and he developed a fix. He couldn't publish it under his name, so it's just called a student t-distribution, or the t-distribution. And I want to start by kind of summarizing a little bit the properties of a t-curve. The book goes into this in more depth than I do. We're just going to do the real basic properties here. So first, it's a probability distribution, just like a probability density function, just like the normal curve. The total area under it is 1, just like with the z. It looks a lot like the z-curve. In fact, by hand, I can't really do the difference. The real difference is that the t-curves have a little bit more area in the tails. What's going to be problematic is there's only one z distribution, the standard normal distribution, and any normal distribution can be converted to the standard normal by using z-scores. We can't do the same thing with t-curves. They are going to be different. Now, we could say they're different for different sample sizes, but t-curves are defined by their degrees of freedom. Degrees of freedom is just the sample size n minus 1. The idea here is if you know what the mean is, and you know the first n minus 1 observations, you automatically know the last one because it has to be whatever value will give you the mean. So that's just kind of the idea of degrees of freedom. It's just one less than the sample size. If you have large samples, like if you do a sample of, 3,800 individuals, with that big of a sample, your t-curve is going to be basically identical to the z-curve, and there's no issues. It's for smaller sample sizes, like 100, or certainly in values less than 100, you have different critical values that we're going to use. Idea is the higher the degrees of freedom, or that means the larger the sample size is, the closer to the z-curve. Basically, all this means we can't use table 5. When we're doing stuff with the t-distribution, when we're trying to estimate population means and make confidence intervals for population means, we're going to have to use table 6, which gives us critical values for our t-curve. Okay, so for examples 1 and 2, we're just going to look at this table and figure out how to use it. All right, the general idea is going to be that try to sketch something again. It's going to look just like the z. Zero's in the middle. This right tail area is going to be alpha over 2, and the table is giving us the t-values that separate that right tail area from the rest. We need to know two things. We need to know what alpha is, which alpha actually is the significance level. We can figure out alpha very easily. Whatever the confidence level is, alpha would be the difference from 100%. So in this first example, we're trying to find t sub alpha over 2. If the confidence level is 95%, that means alpha is 5%, or alpha is 0.05. We don't need alpha, we need alpha divided by 2. So I want to find the t-value so that the area to the right of it is 0.025. And I use this notation. The sample size is 40. That means the degrees of freedom would end up being 39. So some people use a notation similar to this. You'll see me do that just to tell you guys, hey, this is the t-value with a right tail area of 0.025 and 39 degrees of freedom. So let's find this. Here's table 6. And again, it's the area in the right tail, and the table's given us the t-value. We had 39 degrees of freedom, so the degrees of freedom are along the first column. The right tail areas are along the top row. We need our right tail area to be 0.025, so this is what we need the tail area to be. We need 39 degrees of freedom. So we're going to go down this guy. Here's 39 degrees of freedom over this one. And they meet right here at 2.023. So that's my critical t-value. 2.023 is the value that separates the right top 2.5% from the bottom 97.5%. Right, and that's a little bit different. If we were using the z-curve, we would have got 1.96. Here we're going to have a little bit bigger value because again there's more areas in the tails of the t-curves. Right, so example 2, we're going to do the same thing, but we want our confidence level to be 98%, which means alpha is 2% or 0.02. Therefore alpha over 2 would be 0.01. So we need the t critical value with an area to the right of 0.01. Degrees of freedom is always one less than the sample size, so 80 degrees of freedom. All right, so for my 80 degrees of freedom, we're going to scan across, and we're looking for 0.01 as the tail area. And they meet at 2.374. So the critical t here would be 2.374. So you have to do a little bit more work to find these critical t values, but it's not too bad. Other than that, most people think doing this estimating a sample mean is nicer and easier than estimating a sample proportion. So hopefully you feel the same way. Okay, so in the note template there for this, we've skipped over our confidence interval formula and the margin of error formula for a mean. Let's jump right into an example where we apply that. So in a sample of 32 students at a college, the mean GPA is 2.46, standard deviation is 0.94. Construct and interpret the 90% confidence interval for the true unknown population mean GPA. So what I'm going to do is I identify, if this was a test question, it comes right out and tells you you're trying to estimate a population mean, find a confidence interval for it. So copy down the confidence interval formula. Typically for these problems, we're going to be given several of our values to plug in. We know the sample mean GPA is 2.46. Let me skip over the critical t value for a second. We know the sample standard deviation is 0.94. And we know that our sample size is 32. We just have to find the critical t. So off to the side, I'm just going to note that if it's a 90% confidence interval, that means alpha is 10%, so 0.10. Alpha over 2 would be 0.05. So I'm looking to match the right tail area of 0.05 with 31 degrees of freedom because I have to take my sample size and minus 1 from it. So 0.05 for my right tail area with 31 degrees of freedom. I'm getting 1.696. Now this part of the formula right here, that's your margin of error for these problems. Estimating a mean and estimating the proportion, it's the same idea. You're just trying to come up with your sample statistic and then add and subtract a margin of error. Another note I'm going to put here is if you're ever asked to do the point estimate, the point estimate for a population mean is simply the sample mean. All right, so here's our point estimate right there, and then we add and subtract one margin of error. Okay, so I'm going to punch up that margin of error on the calculator. 1.696 times 0.94 divided by square root of 32. And let's suppose on this one we're just going to do 2 decimal digits. Again, you're always safe to display them all. But let's say I want to round this off to 2 decimal digits. So punch this up sometime. If you don't have your calculator now, do this when you look back on it. Make sure you're getting 0.28. And then it's the same logic. If we subtract that, we're going to end up with 2.18. If I do the 2.46 and I add the 0.24, we're going to end up with 2.74. There is my 90% confidence interval. Now, what the textbook does sometimes is they say lower bound 2.18, and then they say upper bound 2.74. I mean, that's technically correct, but I like putting it together in an interval if it's called a confidence interval. So just like with proportions, we're always going to interpret one of these. All right, so our interpretation is going to basically sound the same. We're going to state the confidence level. So with 90% confidence, the population mean GPA is between 2.18 and 2.74. Now, I guess they're called GPA would be in points. Typically, you want to put the unit, so if this is a measurement of length, we need to put whether it's measuring in feet, miles, or centimeters, or whatever. So here, you'd probably get away without the unit here, because GPA is sort of its own unit, but I'm going to say, with 90% confidence, the population mean GPA is between 2.18 and 2.74 points. All right, again, confidence interval means the same thing here. It's the long-run success rate. So if we went out and collected different samples of these college students over and over and over and over, each one of those samples might create a different sample mean. We might get a different confidence interval. A bunch of those intervals are going to cover the true mean. If it's a 90% method, about 90% of them will cover the true mean, and about 10% will miss. Also, just like with the proportions, if we want to increase the confidence level from 90 to 98, we've got to give ourselves a longer confidence interval. I'm going to have to drop down below 2.18 and go up above 2.74 for this. So it says redo the example using a 98% confidence level. Well, look at what's not going to change. The sample mean's not going to change. The sample standard deviation is not going to change. Our sample size is not going to change. The only thing that's going to change is our critical t-value. If it's 98% confidence, alpha is 2% or 0.02. Alpha divided by 2 would be 0.01. The critical value with a right area of 0.01 and 31 degrees of freedom. Right, so 31 degrees of freedom and a 0.01, that's giving me 2.453. So again, all I did, same thing, match the degrees of freedom up with the right tail area. But before I had 1.696, here I have 2.453. So when we punch this up on our calculator, the margin of error has gone up. It was 0.28 last time, now it's 0.41. Now let's see, if we do our subtracting, 2.46 minus 2.41 would be 2.05. And if we add them, that's 2.87. Again, we had to get a bigger interval. We had to go down below the left endpoint and up above the right endpoint. The interpretation would sound the same, except with 90% confidence, the population mean GPA is between 2.05 and 2.87. So the only thing that would change are the specific numbers. So here's the general rule there, just so you can write it down. If the confidence level goes up, the margin of error goes up. And your confidence interval gets longer, or wider if you want to say wider. All right, so let's take a look at another one of these. What I'm going to recommend you do for this one is try this on your own. So in a few seconds, pause the video and just see how far you can get. If you get stuck, start playing the video again. If you think you can get it through to the end, start playing the video to check your answers. So put it on pause, see how you do. Okay, so let's see how you did here. It says in a sample of 101 batteries used in a distance finder, the mean battery lifespan was 7.2 hours with a standard deviation of 1.3 hours. Give the point estimate. Well, a page or two ago I said the point estimate for a population mean is going to be the sample mean. And that would be it. We're done. X bar is 7.2 hours. End of story. Point estimates are great problems usually. Now though, construct and interpret the 95% confidence interval estimate for the true unknown mean battery lifespan. So again, that kind of tells me that I have to use my confidence interval formula for a mean. Okay, so it's x bar plus and minus t sub alpha over 2 times s over radical n. Every problem you do from the homework or just practice for the test problems, every one of them, write that down. The more times you write these down, the more comfortable you get with them. So let's see, we know 7.2 is the sample mean. 95% confidence, so alpha equals 0.05. Alpha over 2 then would be 0.025. I got to find the t-value so that the area to the right is 0.025. The degrees of freedom would be 100. Here's what I'm going to ask you to do. If you have a problem where the degrees of freedom are not in our table, just go with the closest degrees of freedom. I think our table has 100 degrees of freedom in it. It starts counting by tens at 40 and then it hits 100. So we want to match this up, 100 degrees of freedom with 0.025. So we're going to scroll over. I think this row right here is 0.025. Scroll to the top. Nope. I want the next one over, 0.025. So we got our 1.984. All right, so 1.984 is our critical t-value. Our standard deviation in the sample was 7.2 over the square root of 101. All right, punch this up on the calculator because mistakes happen. Let's go with 2 decimal places again. Again, show me all of them when you're doing the workout. But I might tell you to round something off. And as long as you show me, a bunch of decimal digits, I usually don't mind if after you show me them, then you go to something rounded. Okay, so if we subtract to find the left endpoint, I'm getting 6.94. And if we add to the right endpoint, that would be 7.46. But I always want to do my interpretation, right? So with 95% confidence, the true population mean lifespan is between 6.94 and 7.46 hours. Right, so if you got that right, congratulations. Usually people need a little bit more time than that to get used to this. If you got part of the way, that's about right. Sooner or later you'll start doing fine with them. Okay, next example here, I like it a little bit better. I think it's easier, but some people find this harder. All right, we're given that the lower bound of a confidence interval is 34.5. That just means that's the left endpoint. The upper bound is 42.7. That just means that's the right endpoint. And we need to find the point estimate, and then we need to find the margin of error. Keep in mind a confidence interval is centered at the point estimate, and then it goes one margin of error above, one margin of error below. The point estimate will be the center of the confidence interval. So let's just take the average of the two endpoints. The average of the two endpoints will be our point estimate. So in this case, we're going to end up with 77.2, so divide that by 2, 38.6. That would be our center. So if this was a confidence interval for a population mean, that 38.6 would be our sample mean, x bar. Now the margin of error. Remember, you center an interval at a point estimate. You go one margin of error above it and one margin of error below it. So a confidence interval, if you take the difference between the endpoints, that's two margins of error. So the difference of the endpoints divided by 2 is going to give you your margin of error. That's the way I like to do it. There are other ways to do it, though. If we trust our 38.6 is right for the point estimate, you can do the point estimate minus the left endpoint. That would give you the 4.1. You could do the right endpoint minus the point estimate. That would also give you the 4.1 as the margin of error. But anyway, that's, going backwards, you can always take a provided confidence interval and analyze it to figure out what the point estimate was and what the margin of error is. All right, last problem here, then you can kind of take a breather and see how some of the homework goes. Again, just like with the proportion, we might want to be able to determine how large of a sample we need to obtain a certain margin of error. So a poll asking single adults for the number of hours spent watching television per week indicates that the standard deviation is 7.5 hours. How many people would be needed to estimate the mean time spent per week to within 2 hours? All right, well, with proportions, you have percentages, but with means, you just have values. So within 2 hours means our specified margin of error is going to be 2. So in your note template, you should see the formula. We have to use Z here. We can't really use T because we don't know what the sample size is going to have to be next. So we take the critical Z times our standard deviation divided by the specified margin of error, and we square that. Now there's one missing part to example 7. I wouldn't know how to do this because there needs to be a specified confidence level. I'm always going to tell you guys what confidence level to use. So let's add that in. 95% is going to be our confidence level for this problem. Okay, so if it's a 95% confidence level, it's going to be 1.96 for this Z. Again, I know that because I do this enough, I remember that, but you can go back to table 5, and on the bottom of it are the critical Z scores. Our sample, or our estimate for the standard deviation there is 7.5. We want our margin of error to be 2. Same thing as before, we're going to round up. So I punch this in my calculator like this, parentheses, 1.96 times 7.5 divided by 2, end parentheses, and then either hit your square button or just caret 2. I'm getting 54.0225, but again, it doesn't matter, 54 point whatever means 55 or more. We're always going to round up to the next whole number. Okay, so a lot of stuff to take a look at in this section, in this chapter. One of the things that will also get added to this is going to be how to do this on Minitab. So for now, focus on doing this by hand, but available soon will be information on using Minitab to do confidence intervals. All right, good luck.